One of the various factors in the geometric design of highways and railroads are vehicle kinematics. We design the sight distances basically because vehicles are moving. And in this video, we are going to tackle about vehicle kinematics as part of your module 2 or module 3, and it would be on unit 2 before we proceed with the discussion proper of sight distances. So we will be reviewing kinematic concepts and computations. For acceleration and deceleration characteristics of vehicles, large trucks decelerate at a lower rate than passenger cars and will require a longer distance to stop than passenger cars. Let's focus on the first part of the sentence. Large truck decelerate at a lower rate than passenger cars. So if you have a large truck, meaning that will have a large mass, and it will naturally decelerate at a lower rate than passenger cars. When you say deceleration, that is acceleration basically, but then it is accelerating opposite the direction of motion, or it is the opposite of acceleration in that case. And it will require a longer distance to stop that than passenger cars because the mass of that large trucks contains more momentum as compared with smaller, lighter passenger cars. AASHTO recommends a deceleration rate of 11.2 feet per second, which is a comfortable deceleration rate for most drivers. Many studies have shown that the deceleration rate is greater than 14.8 feet per second squared under emergency situations. We will take a look at the graphs shown in the figure. This is the weight to power ratio and the maximum acceleration rate. So we can see here in the first figure that as the weight to power ratio increases, the maximum acceleration rate of that passenger car decreases. It also follows the same with the tractor or trailer trucks for the second image in the right portion of the screen, but then it has somewhat non-uniform change or rate of change. Let's review first uniform acceleration. We know that for uniform acceleration, from the word itself, meaning there is no change in the acceleration. Meaning the fundamental formula from kinetics is F equal to ma, where F is the force in newtons, m is the mass of the object, and a is the acceleration due to gravity in meter per second squared. That is for uniform acceleration. So for uniform acceleration or constant acceleration, meaning the rate of change in the velocity with respect to time is equal to a constant. For example, if the velocity of the car in the figure increases by 2 meters per second every second, then that is an example of a uniform acceleration. Or if it is decelerating at 1 meter per second squared, meaning the car decreases its velocity by 1 meter per second. So let's have this problem. A truck traveling at 25 mph is approaching a stop sign. At time t0 and at 60 feet, the truck begins to slow down by decelerating at 14 feet per second squared. Will the truck be able to stop in time? So Let's try to draw the figure. So we have this, let's assume that it is on a level road. We have a truck. Is that a truck? Yes, a truck is traveling. So we have the truck and it's traveling at an initial velocity of 25 miles per hour, if I'm not mistaken. Yes. V0, 25 mph. And it will decelerate at 14 feet per second squared, or that is a negative acceleration, feet per second squared, before it proceeds with the stop sign. So we have here the stop sign. For example, if that is at t equal to 0, if at t is equal to 0, or the beginning of our consideration, the distance of the front of the truck up to the stop sign is 60 feet. This is 60 feet. And this is the deceleration, negative 14 feet per second squared. Let me try to place this at this portion. Acceleration is at negative 14 feet per second squared. We are asked if the truck will be able to stop in time. So that means that we are asked if the distance of the truck from the stop sign is 60 feet and it is traveling initially at the start of our analysis at 25 miles per hour, and the acceleration will be negative 14 feet per second squared. Will the truck be able to stop in time before, or yes, before it will pass through this, or will it be able to stop before or exactly at the end of this 60 feet mark, and that is on the stop sign? So if the front of the truck will be able to end at this point, then it will be safe. It is able to stop at before it will be able to pass through the stop sign. But if the truck will be able to have a will have a velocity of greater than 0 at this point, then that means that the truck will not be able to stop in time. So for that, we have constant acceleration and we have the velocity. We have the distance here. We will use kinematic equations to solve for the problem. So to do this, we will be using this formula from your kinematics, from your dynamics of rigid bodies. Velocity final, or let's just say V squared, is equal to initial velocity squared plus 2 times the acceleration multiplied by the distance S minus the basis, or the original distance. This means S minus S0 means the interval or the change in distance. We can say this as the interval distance, change in distance. We can just say that that would be 60 feet. We will determine what is the velocity of the truck when it will end this span of 60 feet. Okay, so the initial velocity is 25 mph and the final should be 0. So the question in our mind is, will v, or the final velocity, be equal to 0 at the stop sign? Remember that the direction of motion is going to the right. So we have here v squared is equal to v0, or the initial velocity, which is 25 miles per hour. But then 25 miles per hour, let's convert it first into feet per second. We have 25 miles per hour to convert that into feet per second, so that we'll be consistent with our units. 1 mile is equal to 5,280 feet, and 1 hour is equal to 3,600 seconds. And we have your initial velocity in feet per second. That would be, let me use my calculator, 25 times 5,280 over 36,000. That is equal to 36.667 feet per second. So we have our velocity in feet per second will be consistent with our units. This would be 36.667 squared plus 2 times the acceleration, which is negative 14. That is in feet per second squared. So we are being consistent with our units. The change in the distance on which we are considering is 60 feet. So this would be 60 feet. Again, we are being consistent with our units. Take the square root of both sides of the equation. And we will have v equal to 36.6, or the square root of 36.667 squared plus 2 times negative 14 times positive 60. This will be equal to the square root of negative 335.53. What does that mean? This gives us the idea that the truck will be able to stop before it will reach the stop sign. So for us to be able to know that distance from which it will be able to stop, let's say that the velocity final will be 0. So we have the velocity final at 0, that would be 0 squared, equal to the initial velocity squared, or the original velocity, 667, or sorry for that, that would be 36.667 squared plus 2 times negative 14 times the change in distance. So for this one, we have the change in distance equal to negative 36.667 squared divided by 2 times negative 14. And this will be equal to 48.017 feet. Meaning, let me change my pen color. the truck will be able to stop 2, 4, 6, somewhat at 1/3. Say this is at 48. This is 48.017 feet. This means that the truck was able to stop prior to reaching the stop sign. Okay? So that is for uniform acceleration. For non-uniform accelerations, we need to consider this because in real life, there is really no vehicle that travels at uniform acceleration. There will always be a change in acceleration. And one condition that we can do is that we can relate acceleration in proportion to speed. Here, we can relate acceleration in proportion to speed. Okay, and the specific case is to vary acceleration inversely to speed as noted. So for this one, we will use this formula. The derivative of velocity with respect to time is equal to alpha minus beta times the velocity. V is equal to the velocity and t is equal to the time or the time interval. In here, a and alpha and beta are constants. They are given in the problem. So from that initial formula, we can inspect that from the equation, alpha indicates the maximum acceleration attainable. Meaning, that is the maximum acceleration that the vehicle will be able to attain. Beyond that is impossible. So for every vehicle, there is always a different value for alpha and beta. And it will be given in the problems that will be given in your activities. So, you will integrate the equation between v or the final velocity and vo or the v0 or the initial velocity. So let's try to do that. Let's try first to cross multiply these two for us to easier integrate, and we will have dv over alpha minus beta v, and this will be equal to dt. So integrating both sides of this equation from v to v0. So if you will notice, from our differential or integral calculus, we say that the integral, recall that the integral of du over u is equal to the ln of u plus c. Then let's evaluate our given here. We have here u, but the derivative of u is not equal to the numerator. So what we will do is we will introduce a constant outside the integral sign, and that would be, so let's evaluate this one. We know that we can say that u is equal to, or let me place that one here. We know that u is equal to alpha minus beta of v. Take note that alpha and beta are constant, so we don't have a problem with that. And du is equal to the derivative of alpha is 0, and the derivative of negative beta times v is equal to negative, or the differential rather, this would be negative beta dv. So let's try to use this one. This would be the integral of du, that is negative beta dv over alpha minus beta v. And since we added this constant here on our function, we need to place a constant outside the integral sign to balance the integral. So we are not changing the sense of the integral. We are just doing this for ease of computations. This would be negative 1 over b. Because if you will place this outside the integral sign, it will just be equal to 1. Negative 1 over b times negative b, or negative 1 over beta times negative beta will just be equal to positive 1. So we are not really changing the sense of this equation. We have here the integral of the theta, or dt, sorry. So from this one, we can say, or we can interchange this actually. So the integral of dt is equal to t, and that will be equal to, we copy this constant, that would be negative 1 over beta, and the derivative, or the integral of this function inside the integral sign is equal to, following the formula here on the top, that would be ln of u, and u is equal to alpha minus beta times v plus c, if that is an indefinite integral. But then this will be a definite integral because we will be integrating between v and v0. So we will be integrating between v and v0. So continuing, we have t is equal to negative 1 over beta, or we can cross multiply this. Cross multiply negative beta to the other side, and this will become negative beta t, and we evaluate this portion. This will become ln of alpha minus beta v minus the ln of alpha minus beta v 0. So continuing, we have this one, negative beta times time is equal to ln. From the properties of your logarithms, we can say that if you will multiply these two, this is equal to ln of alpha minus beta v over alpha minus beta v 0. So from here, we can use the constant e to eliminate the natural logarithm. That would be e raised to negative b, or beta times t. That is equal to e times, or e raised to ln of alpha minus beta b divided by alpha minus beta v 0. These two are equal, so we will cancel this part, and we will have e equal raised to negative beta t, and this is equal to alpha minus beta v over alpha minus beta v0. And what we will do here is we will cross multiply this denominator to e times e raised to negative bt, and that will be equal to alpha e raised to negative beta t minus beta v0 e raised to negative beta t, and this is equal to alpha minus beta v. And multiplying both sides of the equation by 1 over beta, we will have alpha over beta minus beta will be cancelled. What's left here will be e raised to negative beta t VO equal to alpha over beta. Oops, I forgot to include the other factor. This will be e negative beta t. And continuing our multiplication or distribution of this factor, this will become simply v, or the velocity. And manipulating the equation, we will arrive with v, transpose this to the other side and transpose these two factors to the other side of the equation, or to the right side. We will have alpha over beta, transpose this to the other side. This will become negative alpha over beta e raised to negative beta times time plus e raised to negative beta times time times v 0. So we can factor out alpha over beta from here, and we are left with alpha over beta multiplied by 1 minus e raised to negative beta t. This will become plus e raised to negative beta t v 0. Okay, and that would be our working formula. For non-uniform acceleration. So we have it here. Okay, the equation for distance as a function of time is now equal to x is equal to the following formula. And the acceleration time relationship based on this one will become dv over dt is equal to alpha minus beta times v0 multiplied by e raised to negative beta times time t. And we'll have an example problem with this one. An impatient car driver stuck behind a slow-moving truck traveling at 20 mph or miles per hour decides to overtake the truck. The accelerating characteristics of the car is given by dv over dt is equal to 3 minus 0.04 v. So this seems familiar, right? This is the accelerating characteristic of the car. And by correspondence from our formula a while ago, we can say that 3 here is alpha. So let's write it here. Alpha is 3. And beta is now equal to positive 0.04. Because from the formula, it's really negative here. So that's simply positive. So there we have your accelerating characteristics of the car. And v is the speed in feet per second for this formula given. And t is the time in seconds. So we are asked, what is the acceleration after 2, 3, 10, and 120 seconds? We are also asked, what is the maximum speed attainable by the car? And also, how far will the car travel in 120 seconds? So let's try to answer that one. Let's start with A. Or number 1. Is that number 1? No, it's A. So for A, for 2 seconds. Yeah, we are asked for the acceleration after 2 seconds. So let's write the given. We have the initial velocity equal to 20 mph, miles per hour. But then let's convert this to feet per second for us to be consistent with our units. This will become, for 1 mile, there is 5,280 of a feet. And For every hour, there is 3,600 seconds. Okay, so using our calculators, we can say that our initial velocity or the original velocity will be 29.333 feet per second. So we know that acceleration is the rate of change of velocity with respect to time. And we have that formula, dv over dt is equal to alpha minus beta initial velocity multiplied by e raised to negative beta times time. So this is acceleration. Acceleration is equal to alpha is 3.0. Let's just use 3 minus 0.04 times the initial velocity, which is 29.333 multiplied by e raised to negative 0.04 times the time elapsed, which is 2 seconds. Take note that the constant e there is equal to 2.718, and we have the acceleration now. This is equal to, use my calculator, 3 minus 0.04 times 29.333 multiplied by alpha e, or e, raised to negative 0.04 times the time elapsed, which is 2 seconds. This will become equal to 1.686. This is in feet per second squared for 3 seconds, or after 3 seconds. This is, of course, from the start of our consideration. From the start of this, the measurement of this velocity, which is 20 mph. After 3 seconds, we use the same formula. This will become acceleration equal to dv over dt. 3 minus 0.04 times the initial velocity is the same, 29.33 multiplied by e raised to negative 0.04 times the time elapsed, which is 3 seconds. This will become equal to 1.620 feet per second squared. After 10 seconds, of course, still taken from the initial velocity of 29.333 feet per second, the acceleration will become, using the same formula, of course, I will not be writing it anymore. This will become 1.224 feet per second squared, and after 120 seconds, the acceleration is equal to almost 0.015 feet per second squared. So we can see that it really is changing the value of acceleration from 1.686 to 1.62. It further decreased into 1.24, and then further decrease into almost 0 at 0.015 feet per second. So next question is, we are asked, let's go back to that one. What is the maximum speed attainable by the car? So maximum speed attainable. So from our formula, we have dv over dt. This is equal to alpha minus beta v0 times e raised to negative beta times time. We can use optimization in this problem. So we can see that if we optimize this one, the velocity, the rate of change of velocity with respect to time, we will be able to obtain the time in which, or the initial velocity, which is also the maximum speed attainable by the car, because this one is decelerating. So if you optimize, we can say that this will be equal to 0. This is equal to 0. Alpha is 3. Beta is 0.4. We are looking for the initial velocity. And this is e raised to negative 0.04 times time. Time for it to have its acceleration equal to 0, which is the maximum at maximum speed. So cross multiplying this factor, e raised to negative 0.04 times t, cross multiply it to the other side here, it will just be equal to 0 equal to 3 minus 0.04 v0. Transpose to the other side, this is negative 3 equal to negative 0.04 v0. We have your initial velocity, which is the maximum speed attainable by the car. This will become equal to 75 feet per second. Okay, so next we are asked for letter C. What is the distance? What is x at 120 seconds? So we have the formula. That would be x equal to alpha t over beta minus alpha over beta squared times 1 minus e raised to negative beta t plus vo over beta times 1 minus e raised to negative beta t. And from here, substituting the values, alpha is equal to 3, beta is equal to 0.04, v0 is equal to 29.33 feet per second, and we have the time elapsed at 120 seconds. We will have the value of x, or the distance traveled, to be equal to 7,867.72 feet. So that is how you use the formulas for non-uniform acceleration.